Good evening, everyone, and welcome to the Amateur Radio General Class, session number 13. During our previous session, we discussed quarter wave antenna, ground-mounted radials. We also talked about feed point impedance, other types of antennas such as the random wire, directional antennas. We discussed antenna gain and the difference between dBi and dBd. We also discussed the concept of front-to-back ratio. Then we went into the Yagi antenna, stacking Yagi antennas. Then we discussed feed point matching via gamma match, hairpin match. Then we went on to other antenna types such as the inverted V, the log periodic, NVIS, or the concept of NVIS antennas, what a beverage antenna was. Then we went into a couple other concepts such as harmonic rejection as it relates to multiband antennas. Then we discussed what are traps, and also we discussed other antenna types such as the end-fed half wave, also the magnetic loop, the screwdriver antenna, and then the halo antenna. And we ended, of course, with our usual question pool review. So the agenda for this evening, we are going to be discussing sunspot cycle, solar flux index, or SFI. We'll be talking about band propagation as it relates to the solar cycle. Also, propagation as it relates to the sun's rotation. Then we talk about what SIDS, or sudden ionic disturbances, are and as it relates to solar flares. Also, what are coronal holes and what are CMEs are, or coronal mass ejections. Then we'll discuss the geomagnetic storms, the Earth's K and A index. Also, we'll discuss the concept of maximum usable frequency and lowest usable frequency. Also, automated receiving stations for propagation determination. Then we'll talk about short path and long path propagation. And we'll also discuss atmospheric noise and static. And then we will end the theory talking a bit more about the ionosphere and the various regions such as F2, E, and D. And of course, we will do our usual question pool review that covers all of the topics that we would have covered this evening. Okay, so just a reminder that we are on the general class level. So persons who are seeing this for the first time via YouTube, we are presently in level 2 of the amateur radio course. It's called the general class. However, there is a technician level or level 1 that's available should you choose to. These are the links to access that on-demand course, as well as all of the documentation and handouts and material for that level, the first level known as the technician level. So feel free to avail yourselves. Okay, so just to check to where we are with respect to our curriculum. So we're progressing quite nicely, and we have now started the topic radio wave propagation. Just a reminder, it's never too early to take practice exams, give you an idea where you are and also what's expected of you, what knowledge you need to learn. So please consider taking practice exams. Again, congrats to all who have been taking the practice exams and have been passing quite well. Okay. This is just the Zello slide. It's in your pack. Right, so this particular slide is important for all participants in the general class course, whether you're now joining. All of the documents related to this course are available at this link. It's a cloud share, so we avoid emailing all of these documents. And then we have a playlist of all of the recordings for the previous sessions that we have had. This is session number 13. So all previous videos are available that you could relook if you have already taken the session. And if you have not yet, of course, it's available to you. We know it's not always convenient to be live on a Friday evening with the course. So all of the recordings are there at your fingertips. Please make use of it. And just a reminder, we're using the No Nonsense General Class License Study Guide. We know several students have availed themselves of it, of the text, purchased it from the author. Of course, it's optional for you to purchase anything at all, right? But you can do so on Amazon or any of the other your favorite websites to access any of these texts. Highly recommended, but it's optional. Okay, So let's go into the Q&A from last session. So I believe we just had one outstanding question, and I think this question came from Roger. Very good evening to you, dear Adish. Great to have you. Okay, so Roger asked, what is the distance of the hop with the NVIS antenna? So in other words, when you're using the NVIS concept and NVIS antennas, how far are you trying to reach? Remember we said that the NVIS antenna is such that it's created in such a way that you're looking for fairly near communication. So Roger's asking, well, how near are we talking about? So we have a little map and a diagram that we'll show in the upcoming slide here, but just in terms of, for your information, you can read this through, but essentially it's up to a few hundred kilometers. That's the sort of distance we are talking about. So we'll illustrate that very shortly on a diagram and a map so you can get an appreciation as to what we're talking about. Because on HF communication, we're talking about thousands of miles or thousands of kilometers coverage as the signal bounces into the sky, it's refracted by the ionosphere. And we'll be talking quite a bit about ionospheric propagation this evening. And we reach very large or long distances. And then we have something called the skip zone, as we would have learned in the technician level, where, because the signal is basically flying right over your head, there's an area where on HF, it's a dead zone really. But with NVIS, you can cause the signal to drop short of where it would normally go when it bounces or refracts off of the ionosphere, and that concept is called NVIS. So Roger, to hopefully make this real, we have provided two things. One, this diagram that shows you, so if you are located here on the Earth's surface and this is your transmitter, depending on the angle that your signal leaves, and of course this could be by design, depending on how high from the ground your antenna is, it changes the radiation angle. And if it goes, you could, just up to a couple hundred kilometers. That's the answer to your question. But we have also done a little map here to show what we are talking about, right? So if this is Trinidad and Tobago, we can use NVIS to drop a signal, let's say maybe to Tobago, or maybe to St. Vincent and the Grenadines, or Grenada, or Barbados, or St. Lucia, right? So NVIS can be used on those low parts of the HF frequencies to have propagation that would probably otherwise not have made it to the short hop. It would have gone all over via the ionosphere into thousands of kilometers away, but NVIS will allow us that sort of short drop, or to drop the signal closer using this NVIS technique. So hopefully this diagram illustrates the distance, and this map gives us an idea of what we probably could achieve using NVIS. Excellent question there, Roger. All right, so and we just repeated this slide as to what NVIS was and how we construct NVIS antennas and what we're trying to achieve. Okay, NVIS, we're dropping the signal short as opposed to the usual angle of radiation that causes our signal to go very far across the Earth and even bounce, something called skip, right? It's reflected many times, reflected and refracted, okay? All right, so what are we really trying to achieve when it comes to our radio communications, especially on HF? We are trying to bounce our signal off of the ionosphere. And we say sometimes it's reflected off the ionosphere, but what it's really doing is being refracted, it's being bent into that region. So you have the troposphere and you have the ionosphere, and that radio signal that leaves your antenna will go to the ionosphere and bounce onto the Earth. And it can hop several times. So that's what we're actually trying to achieve with our HF communication. So let's just bear this in mind as a diagram, what we're trying to achieve when we're talking about HF communications. Okay, so we're now going to talk about the sunspot cycle. So all of us should be quite familiar with what the sun is, but do we know, or did we know, that the sun has spots? Yes, so here's a picture of the sun. Now remember, you don't want to look at the sun directly, and certainly you don't want to use any optics to look at it at all. There's a safe way to observe it, but please bear in mind, you don't want to go looking at the sun to find, can I see spots, right? If you're doing so, do it either having been trained or with someone who is duly trained to take those pictures or to look at it, right? But just please save your eyesight, don't just go looking up at the sun. But take our word for it, the sun has spots, and these spots come and go in a 11-year cycle. As a matter of fact, right now, we're in cycle 25, and we are actually increasing in that cycle, and we're seeing a lot more sunspots. Matter of fact, out of them, we're getting quite a few solar flares that are being generated, and we'll be coming to what solar flares are and so on. But just note that every 11 years, and we have a diagram that shows that every 11 years, there's a peak and a trough, that sort of cycle. And sometimes the peaks are a little higher than other years. So we have from 1750 all the way to present time, the sunspot cycle. So it shows generally there is in fact about an 11-year cycle in terms of the sun activity, all of that magnetic activity that leads to sunspot formation, right? So the sunspot appear as darker or cooler areas. Now they're still very hot, but they're just relatively cooler in the sense that, these magnetic fields that pull the material back inside, causes it to appear a little cooler than the rest of the sun. So it's very hot still, but you can actually see it if you look at this diagram here, this picture, actual sunspots on the sun, right? Okay. Now, we need to be aware as amateur radio operators that sunspot cycle and these sunspots play a very critical role in our HF communications. It can enhance, when sunspots are around, our HF communications, because the particles that are emanated can in fact assist in causing our ionosphere to be in such a position or activation that it will allow our signals to be bounced even better than it would be when we have the low part of the sunspot cycle. So right now, cycle 25, if you were to look on the right-hand side here, we are sort of going towards the peak. We're not quite yet at the peak, and we are actually above the average. So if you look at the red line here, this is what we're expecting. This is the band or the range as expected or as predicted, but we are actually consistently, since the start of cycle 25, it's actually above. So pretty good activity, very important to amateur radio operators. And of course, literally, we're making hay while the sun shines. So we need to know for the exam that the higher the number of sunspots, it generally indicates a greater probability of good propagation at the higher frequencies, or HF, right? So this is an exam question. Sunspots are our friend, generally speaking. Okay, so to get a sense or to gauge or to measure what the sunspot number of sunspots, the activity level of the sunspots, how strong they are, how big they are, how many they are, or how helpful they are, we have to measure it. And one of the measures of the number of sunspots that will help us as amateur radio operators, we look at the SFI, or Solar Flux Index, right? So we have, apart from just the pure number of sunspots, we have this Solar Flux Index, and the Solar Flux Index also mirrors the number of sunspots, right? So SFI is something that we do look at, and for the exam, you need to know that the solar radiation is measured in the 10.7 centimeter wavelength, right? So this is an exam question. So learn this for the exam. So you have the solar flux index as well as the sunspot number, very much related to one another. And we have here on the diagram, this is actually, this was taken maybe a little earlier today, the actual solar flux index. And this is, we are current here. We're not yet at the peak, but notice we are above. This graph here shows the actual, and this here shows the predicted, and we are above the predicted. So a pretty active cycle 25 indeed. Right, so we also utilize those numbers to be a predictor of propagation. We want our radio frequency to propagate through the go through the sky to the ionosphere and bounce back, and that propagation, or that movement of our radio signals that leaves our antenna on the HF part of the spectrum can be predicted based on those elements, such as where we are in the sunspot cycle, the sunspot numbers, the solar flux index. And on your screen is an example of something that we look at. It's a nice chart that gives you quite a lot of information here. So you'll notice solar flux index is there, SFI, and this, by the way, was actually taken a little earlier today, 12th of January 2024. And it also shows you for your HF part of the spectrum, the different bands, the 80 to 40 meter band area, 30 to 20, 17 to 15, 12 to 10. During the day, whether propagation is good or bad. During the night, whether propagation is good or bad. So we do look at these things and determine, are we likely to have good propagation and therefore good operating conditions that we can get on the air and communicate with our fellow amateur radio operators. Right? So, of course, there are a couple of exam questions that we need to be aware of. That one of them will be the 15, 12, and 10 meter bands are the least reliable for long distance communication during periods of low solar activity. So right now we have high solar activity, but during low periods, when we're in the doldrums or the trough of that cycle, 15, 12, and 10 are the least reliable for long distance communication. So you need to learn that for the exam. All right, so we did say that the sunspots on the sun exist, comes and goes during the sunspot cycle. But what we also need to know, the sun is also spinning, or it is rotating really. And because of that rotation, the sunspots also rotate in and out of views. And the sunspots areas actually have numbers as well, right? So they rotate in and out of view, and of course they increase and decrease and so on, and they move. So for the exam, we need to know that one of the things that affect our radio propagation is in fact this rotation of the sun on its axis. And because of that, the surface layers, which is where you will see the sunspot, they go in and out of view approximately on a 26 to 28 day cycle, and that causes our HF propagation to vary periodically, right? That's because the sunspots are coming into view, and then they're going out of view, going in, let's say, the far side of the sun that the earth would not see, right? So it spins or it rotates, and that causes our propagation to also vary. So exam question. All right, so our sun, because it's very active, you will from time to time have what are called SIDS, or sudden ionic disturbances, as a result of solar activity. And one of the key activities that take place on the sun, and they're usually associated with coronal holes or sunspots, are called solar flares. Now, a solar flare, if you were to look at the diagram here, you will see this bright spot on the picture. That's actually a solar flare, and it's actually associated with a sunspot. And that sunspot will come into view and go around and make its way and go and disappear again to the back and come around again maybe. So that sunspot from time to time will cause a solar flare to occur. Now a solar flare is radiation, you see it here, it's showing up as a bright light, but it's radiation, ultraviolet and X-ray radiation, and that moves very quickly out from the sun towards Earth, for example, and it actually gets here on Earth in about 8 minutes time. So once there's a solar flare, within 8 minutes, those ultraviolet and X-ray reach us and cause disturbances and affects our propagation, because those particles affect the ionosphere as well as the geomagnetic aspects of the earth, right? So we need to be aware of the sunspot cycle. We need to be aware of solar flares. We need to be aware for the exam how long it takes, and we have it here as a bullet point. It travels at the speed of light. That's UV, and X-rays will travel at the speed of light and get to us in 8 minutes time, and it will usually affect radio wave propagation. If it's depending, it could last for several minutes. And on the right hand side here, we are showing an example of one of the real-time pictures that show, okay, this is the sun-facing part of the earth, and as a result of this solar flare, we have a radio blackout that's going on here, and that's part of the earth, right? And it affects the entire earth generally, but you know, it's only a part of the earth at any time is facing the sun. So this is where will be significantly affected, and by virtue, because amateur radio signals bounce all over the earth, it affects, you know, global propagation. But this just shows here the sun-facing aspect of part of the earth at the point in time that that solar flare occurred, and you see these diagrams. All right. So because the solar flare can create radio blackouts, that's very significant, and we need to be aware of that. And the effect can be greater on lower frequencies rather than higher frequencies. And of course, the sun-facing side of the Earth, meaning daylight or daytime, you can have very severe radio blackouts, again in the HF part of the spectrum and the lower part of that spectrum as well. So these are all exam questions on your screen. We have some pictures that just sort of illustrate what a solar flare looks like. We see that it's leaving the sun. You have the UV rays and the X-rays that come, and of course it causes these layers in the ionosphere to absorb radio frequencies, right? So that's what causes the radio blackout. So you have the different levels or layers of the ionosphere, which we talked about in the technician class, and we'll discuss a little bit further shortly because we need to know some properties about those various layers, right? So sudden ionic disturbances due to solar flares. Right, so another aspect of our sun that we need to be aware of. So apart from solar flares, now solar flares get here in 8 minutes. It's a very bright occurrence. You know, you will see it very bright presence on those pictures that we showed you there from the SDO. But we also need to be aware that those areas of the sun where you will have coronal holes, and you can have what is called CMEs, or coronal mass ejections. Now, what a coronal mass ejection is actually the sun ejecting or emitting part of its content into space. It's basically throwing up, it's just pelting out literally some of its content, right? Quite a bit. And you have a picture here of a CME. So this is the sun, and this is a coronal mass ejection. It just ejects those particles. And some of these CMEs could be Earth facing, right? So if Earth is in the direction of the CME, well, it's going to come at us. If it's not directed directly at Earth, some of it may reach eventually, but we will tend to be more concerned about when it's an Earth facing type of CME, or what you call a 360 halo, right? When it comes straight at us, right? It will affect our Earth's magnetosphere or geomagnetic spherical, you know, the Earth is protected by a magnetic field. So that CME can come and have disruptions to it, and which will also cause radio wave propagation effects. So we need to be aware that these CMEs, when they get here, they are charged particles that arrive, and therefore they affect the ionosphere, it affects the magnetic properties of the Earth's magnetic field. So unlike the solar flares, that the UV rays and the X-rays, they're traveling at the speed of light, they'll get here in 8 minutes. A CME are really charged particles, so it does not travel at the speed of light, right? So they take much longer to get here, and they can take anywhere between 15 hours to several days to get here. So they're not as quick to reach us as the solar flare, the UVs and the ultraviolet rays and the X-rays from a solar flare will take, right? It's much slower, these CMEs, to get to us. I mean, they're still pretty fast, but several times order slower than the solar flare. So that's one of the differences between a solar flare and a CME. You know, sometimes people think it's the same thing. It's really not. They can be related, because sometimes areas that there are existing solar flares, you can have a CME from them, right? So they can be related, but we don't want to mix them up. As amateur radio operators, we need to be discerning, we need to be aware of the differences, and of course your exam questions will require us to know the difference between the two. So that's why we're taking the time to show, compare and contrast the differences. Okay, you need to know this for the exam, that the CMEs, or the coronal mass ejection, that's ejected by the sun, will take 15 hours to several days to reach us, right? And of course, when it reaches us, AHF radio propagation is affected, just like solar flares, right? When solar flares get here, when the UV and the X-rays get here, just the same way, when these particles reach us from a CME, they also affect HF communications, right? Become disturbances, right? Okay, so as a result of CMEs, or even this just the solar wind. So you'll see here we have the sun, and the sun is letting off a continuous stream of the solar wind, and that solar wind is exacerbated where there are these coronal holes. It allows more charged particles to leave the sun. The sun is actually sending that out throughout the entire solar system, but Earth is there, and of course we have our magnetic field that's protecting us, but it's the sun itself is sending out all of those charged particles continually, right? So it's not only when the CMEs eject it, but the coronal holes also eject those particles continuously as well. And when there is a CME, it exacerbates, and of course that causes what you call a geomagnetic storm to occur, and you need to know that for the exam. And when that occurs, we have degraded, especially at the high latitudes on the Earth, degraded HF performance, because propagation is affected by those charged particles as it affects the magnetosphere of the Earth, right? Now, while it does that, as hams, you may recall from the technician class, we said that hams, we love to bounce our signals off of things. We'll bounce it off of our water tank for VHF communication. We'll bounce it off of the moon with EME, or Earth, Moon, Earth, or what we call moon bounce. We try to bounce it off of the trails left by meteors and what we call meteor scatter. You may remember some of those. You may also recall that we try to bounce our signals, especially VHF signals, off of aurora. So we have aurora borealis, or the northern lights, and we have aurora australis, or southern lights, that's created whenever we have that sort of geomagnetic disturbance. Pretty looking lights if you've ever seen it, but hams can also utilize this and bounce our signals, particularly in the VHF part of the spectrum, such that our signals will go up and bounce into another part of the Earth that it would not have otherwise been able to through line of sight. It will go up into the sky, bounce off the aurora, and drop on another part of the Earth and allow us as hams to communicate, because as hams, we love to bounce our signals off of things. So we can have a benefit, notwithstanding the geomagnetic storm can have disturbances. It can create aurora, especially the high altitude, high latitude parts of the Earth, and we can benefit from that. So that's another exam question. We can use the auroras that formed from the geomagnetic disturbances or the geomagnetic storms that's caused by these CMEs and just the solar wind itself when it's very strong, to benefit radio communications, because we will reflect our VHF signals off of it and communicate longer distances. So we have a slide now that just sort of compares and contrasts some of these space weather related activities. So you have the UV and the X-rays that will be emanated from solar flares. You have the usual solar wind. You have a CME, and you have different timelines as well. So this is just for your information, a slide I thought that would be useful for us to compare and contrast, that the particles or the emanations from the sun do take a different different times to get to us depending on what it is. So if it's UV and X-rays, that's traveling at the speed of light. But if it's if it's a coronal mass ejection or just the solar wind, it will take several hours to several days to get to us, and so on. All right, so we did talk about the geomagnetic aspect of the sun affecting us, but how do we measure it? How can we tell, hey, the sun is affecting us now, and there's a geomagnetic storm? How do we know? What can we measure? Well, there are two indices that exist. They have detectors, different parts of the globe that detect these the presence of particles, and one is called the K index and the other is called the A index. It basically checks and monitors the Earth's geomagnetic field, right? So we need to be aware that there's one called the K index, and the K index looks at short-term stability. So that's the key there for K index. The A index, on the other hand, however, looks at the long-term stability, right? So K index short term, A index long term. And we just have a little chart here to give you an idea of the A index and the K index, what it means when it gets to a particular value. Right? So notice here it's pretty quiet. We have a minor storm, major storm, severe storm, very major storm, hopefully. Right? So these are all possible, right? And space weather is something as hams we should pay attention to. And these are some of the charts that you'll see, the K index. Notice here where there's a storm here. Look at this, it's gone to red, orange, and so on, right? And we have the A index as well. So again, A index is the long-term stability, and the K index is the short-term stability. We tend as hams to pay close attention to this. Exam questions: K index, A index. All right, so we probably just do a couple more slides, kick off this section, and then we'll probably take a short break. All right, so we need to be aware. So remember, when we said as amateur radio operators, what we are trying to achieve, let's go back to a couple slides back. What we are trying to achieve is communicating from one part of the earth to another amateur radio operator on another part of the earth using our radio transceiver with our antenna to cause our wireless signal or radio signal to go into free space, go all the way up past the troposphere, all the way to the ionosphere and bounce, especially if it's HF that we're talking about, right? That's what we're trying to achieve. So let's just bear that in mind with our conversation. So this diagram here shows that we are transmitting and our signal is going and it's going to come across to another part of the earth here, maybe several thousand kilometers away. And we're trying to communicate with another licensed amateur radio operator. But of course, we have a range of frequencies that we can use, right? We have AHF, VHF, UHF, and so on. And even within the HF part of the spectrum, we have the lower part of the HF spectrum, we have the higher part of the HF spectrum. And depending on the time of day, depending on the frequency we use, when we transmit using our antenna, that signal can either do one of three things. The signal will either go all the way up into the sky, past the troposphere, go all the way to the ionosphere, and either punch through the ionosphere and go out into space, or the signal will go all the way until the ionosphere, and then go no further. It will be absorbed at that layer, or it will be attenuated at that layer, and it goes nowhere elsewhere otherwise. A third option for that signal is that it can go all the way to the ionosphere and then bend or bounce or reflect, or the correct term really is refract. So it's bent in the ionosphere and then bounce back down to Earth to communicate, and it can skip and bounce and continue to do that. So we need to be aware as hams that not every frequency will attain this bounce or this reflection or this refraction really. We need to, as discerning hams, know what frequency we need to punch into our radio. We need to use our dial and put a particular frequency in to achieve this performance, because a frequency higher than that may go straight through. A frequency lower than that may in fact be absorbed. So we have terms for those frequencies. One is called the MUF, or the maximum usable frequency, and what that is, you need to know for the exam, is the highest frequency that you can use to communicate between 2 points. In other words, if you go higher than that frequency, you will not be able to communicate because it will go out into free space. The lowest usable frequency, or the LUF, is the lowest frequency that you can use to communicate between 2 points, because any frequency lower than that may be absorbed. So you actually need to select a frequency between the MUF and the LUF, between the maximum usable and the lowest usable. And that's, as a ham, you will need to be aware of what is that upper and lower range. And of course, there are several things that determine that MUF, right? And we'll come to a slide shortly that tells us those things. As discerning hams, that's why we are trained. We learn to understand these things so that we are able to optimize. We don't just go up on a frequency and start to talk and hope for the best. Yeah, you can do that, yes, but we can be a little more deterministic than that. We can engineer and say, hey, this is the time of day, this is the sunspot cycle, let's go on this frequency, and we stand a chance of being able to communicate. We look at some other propagation figures and we make some decisions. So we need to know about the MUF and the LUF. So at this point, I think it'll be a good time to take a short 2-minute break. So let's do that. Probably get up, take a little stretch, maybe have a bathroom break, get some water, and we'll meet you back in 2 minutes time. Okay, welcome back everyone. So it is indeed amazing that as amateur radio operators, we can communicate across the globe without fiber optic lines, cell towers, and so on. We are able to just use our radio equipment, power it, and an antenna, and have our signal traverse all across the globe. But of course, those signals travel or propagate differently depending on the time of the day, sunspot cycle, the frequency. So that's also one of the reasons why, as amateur radio operators, we have access to quite a bit of spectrum across the radio frequency bands, right? That's one of the reasons. So we can choose the band based on the conditions that exist. So that's why we're also frequency agile, to be able to move and choose those frequencies that will allow our signal to propagate properly. And this is why we go through this training, so that we can understand how and what we need to do to optimize our signals so that we are heard and that we can hear the other amateur radio operator. Right. So maximum usable frequency and lowest usable frequency. Right. Okay, so we did say that we'll talk a bit about the factors that affect the maximum usable frequencies, right? So here they are, and it's in fact an exam question, right? So one would be the path, distance, and location of both the receiver and the sender, the time of the day and also the season. Is it summertime? Is it wintertime? The solar radiation and ionospheric disturbances, right? So in your exam, you will have three options and all of them will be correct. One will be path, distance, and location. The other one will be time of day and season. And the third option will be solar radiation and ionospheric disturbances. So all of these will be correct in the particular question. So you need to learn this, that these are the factors that affect the maximum usable frequency. And if you think about it, the path, distance, and location, yeah, that's what we're talking about. It's two positions on the surface of the earth, how far apart they are, where they are located, what's the path between the two. That affects the maximum usable frequency. Time of day, because when we come to talking about the ionosphere again, the ionosphere itself, the levels or the layers or the regions and how active it is, or the availability to be able to refract the signals, depends or not on the sun being overhead to ionize those particles in the sky, right, and the ionosphere. So therefore, the time of the day is important. And of course, depending on the solar cycle, the number of sunspots, and therefore the solar radiation, and therefore any ionospheric disturbances that may exist. All right. So we have a little formula here for those who are mathematically inclined to show, what frequency we want to be operating in. We need to be operating below the muff and above the luff. So that's where we need to select our frequency. So once we know what our maximum usable frequency is and our lowest usable frequency, we want to choose a frequency inside of there. And you'll see in a little slide a little bit here that the closer to the muff or the maximum usable, that will have the least amount of attenuation. So that may be where you might want to select for your transmission, just below there, because any other frequency will be attenuated more. Again, we'll come to a slide talking about that, but this is just a mathematical representation. This is not an exam really, but for those who, sometimes you want to see it mathematically written down, this is what it could look like. The frequency you choose will need to be below the muff, but above the luff. Right? Also, radio frequency below the muff and above the luff are reflected back to the earth by the ionosphere. This is what we are trying to actually achieve, right? We are actually trying to reflect the signal back down to earth, well, really refract. So once we choose a frequency that is lower than the muff and higher than the luff, then it will be reflected. If it is, we choose a frequency above the muff, it will probably go straight out into space. And if we choose a frequency that is lower than the luff, it will probably be absorbed and go nowhere further, right? So we need to choose that frequency between the muff and the luff, right? Just bear this in mind. It's an exam question. And this is actually the holy grail for HF propagation. We are actually trying to achieve this, okay? This is desirable. All right, so again, just to re-emphasize, what happens if we have a frequency, we punch a frequency in our radio that is below the luff or below the lowest usable frequency? we are going lower than the lowest usable. So what do you think will happen? It will not be usable, and therefore it will be attenuated before it arrives where we want it to, right? So there you go. Exam question. Right, so here's an anomaly. Remember we said that you can have radio blackouts when you have something like a solar flare that will send those X-rays and UV rays to Earth, and it gets here in 8 minutes time. Well, what actually happens at that point is that the lowest usable frequency exceeds the maximum usable frequency, and therefore there are no usable frequencies. Yes, that is what can occur when you have a solar flare an event, right? Those X-rays there will cause or can cause a radio blackout for, sometimes several minutes at a time. And we have a little graph that shows it here, right? It will cause the lowest usable to exceed the maximum usable, and therefore during that period, there's a radio blackout, right? We've just tried to illustrate it here in the diagram where you see the lowest usable. So this is the 24 hours in one day. And at this point, there's a solar flare, and it causes the lowest usable to be greater than the maximum usable, and therefore no communication takes place on that HF part of the spectrum because of that radio blackout, because due to the solar flare and the associated X-rays that emanates. Again, it gets here in 8 minutes. So this is an exam question. For HF propagation, when the lowest usable frequency, that's this, exceeds the maximum usable frequency, that's this, propagation via ordinary skywave communication is not possible over that path, right? So again, that's when the LUF exceeds the MUF. There's no usable frequency for that duration, okay? So hopefully this diagram will help illustrate this text here. Exam question. Okay, moving right along. Okay, so remember we did mention a little while ago that when you're choosing a frequency to communicate on, frequencies just below the maximum usable tends to have the lowest attenuation. So those are good frequencies to choose because it will be attenuated or reduced the least amount, right, compared to any other frequency. So this is an exam question that frequencies just below the maximum usable tend to have the lowest attenuation. Exam question. So therefore, what it implies is when we are selecting a frequency and we want the lowest attenuation, when we are on HF, we just choose a frequency just below the maximum usable. So these two bullet points say just about the same thing. Okay. This is an extra slide really just to let you know about the reverse beacon. So sometimes you want to know, okay, how's propagation going different parts of the earth? Can we communicate? So beacons are one of the ways, so you can read this slide on your own. But let's talk about another way, which is called automated receiving stations. And the one that we're interested in for the exam would be automated receiving stations that's on the internet. And we're just giving you some extra information here. This is a website, pskreporter.info. This actually, I took this screenshot some time ago, and this showed all of the locations that my station would have been receiving signals from at that point in time in the day on a particular band. Right, so this is Trinidad and Tobago here, and notice all of the amateur radio signals that I was receiving at that point from, look, all over the world, right, literally speaking, right? So propagation was pretty good at that point in time, on that day in question, on that time of the day. Right, so this was taken from this website, PSK Reporter. You don't have to be a licensed ham to go and take a look at it. You can go there all now and take a look at how propagation is going between different stations. You could select a particular station and see who that station is receiving, and you can also see who is receiving that station if they're transmitting, right? So this site here. But for the exam, we need to know that a way to determine the current propagation on a desired band from your station is to use a network of automated receiving stations. Those are radio stations all over that when they receive a signal, they will actually send a little report to the internet like this website here, and this website will aggregate, collate, and then have a presentation layer that graphically illustrates these signals to and from. Right, so to the internet to see where your transmissions are being received. So we just give an example here. PSK Report is one of those automated receiving station sites that aggregates propagation data, right? So This is an exam question here. Okay. So now we need to be aware of the concept of long path and short path propagation. What is long path and what is short path propagation? So imagine, if you were, that this is my station located on the surface of the earth here, and I'm trying to communicate with this other radio operator on the surface of the earth, quite a distance away, very far away. So I'm trying to send my signal, my HF signal, to the ionosphere, have it bounce and skip and bounce until it gets to the radio operator here. But notice that there are two ways that this signal can potentially get to this operator. This route, which we'll call the short path, and it can also go the other way. It will go bounce off the ionosphere, bounce off the earth, bounce off the ionosphere, and bounce, bounce, bounce until it gets here also to this operator. Well, there are two ways, right, of the signal getting there. Short path, which is the short version of the route, and the long path, which is the longer version of the route. And we need to know for the exam that the short path or the long path reference to the short path, if we are using directional antennas, if I'm pointing the antenna in this direction for the short path, if I wanted to do the long path, I would just have to turn the antenna the other way or the opposite way, which is actually 180 degrees away from the short path direction. So that's an exam question. For long path contact, I need to point the antenna 180 degrees opposite to the short path. As simple as that, folks. So this is the exam question here, that sometimes the signal can arrive instead via the opposite direction, known as the long path, with the directional antenna pointing 180 degrees from the station's short path heading. So this diagram hopefully will make it real. When it goes this way, it's short path. When it goes this way, which is 180 degrees or the opposite direction, it's the long path propagation. Our signal can go in those two directions: long path, short path. Okay. Okay, so we also need to be aware that there's a bit of a potential issue when a signal leaves one amateur radio operator station and goes both via the short path and the long path, right? It will arrive here, certainly, but because one will be slightly delayed from the other, the operator here that's receiving the signal will hear both. So you'll get a sort of echo effect. You'll hear the voice, and then maybe millisecond after you'll hear the same voice again, and it will sound like an echo. And that is because the signal that's going via the skywave is bouncing off of the ionosphere in one direction and also the other direction, arriving here, but at two different times. Obviously, when it's going via the short path, it will reach quicker, and via the long path, it will take just slightly longer. Yes, it's traveling about the speed of light, but it'll still take a little bit longer to get here. And that is perceived by the amateur radio operator here that's listening or receiving as an echo. So that's an exam question. The skywave signal propagates via both the short path and the long path, and it arrives at the location, which can result in a slightly delayed echo being heard. Right? So exam question. All right, so we're coming now to the concept of atmospheric noise or static. So sometimes as an amateur radio operator, you tune into an HF part of the band and you're listening, and you will hear some noises. Sometimes it can vary, it can be, sometimes it appears constant as well. And we say, hey, we're getting atmospheric noise or we're getting static. So an exam question is that high levels of atmospheric noise or static, and we're saying here it's often caused by thunderstorms, so just that you're aware of it, because lightning like this will release radio frequency, especially in the HF part of the spectrum. And it's typical on the lower HF frequencies during the summer months. Those are the months of June to August in the northern hemisphere, right? So this is an exam question. Okay, so we now come to a couple slides to discuss the ionosphere. So we did talk about the ionosphere during the technician class, but let's talk a bit about it again, and we'll deal with some of the exam questions related to the ionosphere. So let's remind ourselves what the ionosphere is, right? The ionosphere is that those layers in the sky that are formed through the sun energizing or ionizing particles at that layer. And when the sun is overhead, you have different layers being formed. When the sun is not overhead, as in the nighttime, those layers either reduce or disappear completely, right? So it's called the ionosphere, and it's those ionized particles, that's why it's called the ionosphere. They're charged particles that will cause the radio signal to go up to and bounce, and to reach another part of the earth, right? So that is called, sorry about that, right? That is called radio wave propagation. And each layer of the ionosphere is given a different name. So we have the D layer, the E layer, and the F layers. And sometimes the F layer is divided into two. In the daytime, it's the F1 and F2 layer. F2 is much higher, right? Because of the sun during the day, ionizing those particles and causing that layer. And it causes stronger propagation because it's higher and you have longer distances that could be achieved via that F2 layer during the daytime, right? So that is what allows amateur radio operators to make long distance contacts as the radio signal goes up into the ionosphere, bounces or reflects off of the ionosphere. Really, the correct term will be refract. It bends and comes back down to earth. Sometimes it bounces off the earth again and goes right back up, and it bounces and hops and skips just like that. And that's how we communicate with our terrestrial infrastructure. All right. So there are a couple of layers. Let's deal with the F2 layer or the F2 region, right? And during the day, you have the F layer or the F region being split into two, the F1 and the F2. So during the daytime, this F2 layer is present. And for the exam, we need to know that that layer, the F2, is what is mainly responsible for the longest distance radio wave propagation and contacts. And the distance of one of those hops could be as long as 2,500 miles in a single hop. Look at that. That's quite some distance, right? And that happens almost instantaneously at about the speed of light. So 2,500 miles you can cover when your radio signal is going up to the ionosphere and bounces. Once you choose the correct frequency, again, during the daytime, that F2 layer is what allows for that long distance contact to be established. Exam question. All right, so we dealt with the F2 layer, but we also have other layers or regions such as the E layer. So the E layer is comparatively lower than the F layer, if you look at it this way. So therefore, a signal that is bouncing off of the E layer will not travel as far. So we need to know for the exam that the maximum distance that you could achieve via the E region is approximately 1,200 miles. So if you go back to the F2 layer, we'll see the F2 does about 2,500 miles in a single hop. The E layer will do just about maybe half that, 1,200 miles. So you see the importance of daytime propagation on the F2 when it's present. It gives a long, very long distance propagation. Exam question. All right, so we also need to talk about the D layer, which is the lowest layer here. It's closest to the surface of the earth. So you see the D layer, the E layer, and the F layers. Sometimes it's the F1 and F2 in the daytime, and during the nighttime, you just have one F layer here, right? So quite a bit different, the nighttime sky, nighttime ionosphere versus the daytime ionosphere. That's why this diagram on the earth is showing you when the sun is overhead, and then when it's not overhead in nighttime, the other part of the globe, right? The ionosphere is quite different. So it will propagate, yes, but of course we have a difference in the ionosphere during the day compared to the night. And the D layer, we need to be aware, of course, it's the closest to the Earth's surface. You can see that here diagrammatically. D is closer to E than F, right? So that's an exam question. And you can see it here diagrammatically, D, E, F, right? So, okay, and we need to know for the exam that the D layer is the most absorbent of long skip signals during daylight hours. So this layer, the D layer, is what absorbs those frequencies below 10 megahertz. And it also makes long distance communication difficult on the 40, 60, 80, and 160 meter band during the day. So that's why on these frequencies, 40 to 160, hams tend not to use those frequencies, those very low frequencies during the daytime, because that D layer is absorbing those frequencies, right? Exam question. All right, so before we go into the question pool for all of the theory we covered today, just a reminder, we haven't gotten to this section of the courses yet, but there are two questions that have been redacted or removed or withdrawn from the exam, from the question pool, and those are questions G1C08 or Gulf 1 Charlie 08 and Gulf 1 Charlie 10, right? Those are the two questions. We haven't come to it as yet. They're actually on pages 135 and 136 of the No Nonsense License Study Guide. So just bear that in mind, especially if you're taking practice exams. These two will not show up, should not show up in your practice test. And if you're studying, you can safely ignore these. You can read it to see what it was historically, but certainly you don't need to learn or memorize or remember this, because this was recently made obsolete due to changes in regulations in the United States. Okay, so let us now go to our trusty no-nonsense general class license study guide so that we could deal with all of the questions in the question pool that matches the theory that we would have covered this evening. And remember, participants, we are covering every single question that you can possibly get in the exam during this course. So there are no unseen questions, no surprises. You would have covered all. Not only would have gotten to what the right answer is, hopefully we are understanding why the right answer is the right answer for our approach light touch theory with exam focus. That is the methodology of this course, right? Okay, let's go. How does a higher sunspot number affect HF propagation? So we said that a higher sunspot number will generally indicate a greater probability of good propagation at higher frequencies, right? So higher the sunspot, better the propagation. Next question in the question pool. What is the solar flux index, or SFI? Well, it is also a measure of solar radiation, and it uses a wavelength of 10.7 centimeters to determine it, right? So remember, we have the sunspot number, but we also use the solar flux index, and that is an indicator of the solar radiation, and it is measured at the 10.7 centimeter wavelength. Right? So remember, frequencies can be given either in the frequency itself in hertz or in the wavelength. Okay. Hopefully you can see the use of some of the theory we would have covered earlier, right? Why it's important for us to understand these foundational concepts. Let's continue. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? So we say that that band, that 20-meter band, usually could work during the day at any point, right? It's a good band. You'll find ham radio operators using that 20-meter band. That's the 14 point something megahertz. Very popular band for amateur radio operators. You tend to have good propagation throughout. So next up, which of the following are the least reliable bands for long distance communication during periods of low solar activity? So remember, when we talk about low solar activity, let's dissect that question. It means relative to the sunspot cycle, low solar activity. Right now we are in a period of high solar activity. Okay. Which of the following are the least reliable bands, right? So we need to know for the low solar activity period, 15, 12, and 10 meters, those bands are least reliable for long distance communication when we have low solar activity. Okay. Of course, when we have high solar activity, they're very active. Okay. What causes HF propagation conditions to vary periodically in a 26 to 28 day cycle? So let's dissect this question. So you probably already say, wait a minute, 26 to 28 day cycle, that's the rotation of the sun, right? So what rotates it's the surface of the sun, right? And therefore on the surface of the sun, you have those sunspots, right? So that is what is affecting propagation to vary as the sun rotates. Again, it takes between 26 to 28 hours, 28 days, I should say. So it's the rotation of the sun's surface layers around its axis. Okay, let's continue. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? Well, it disturbs or it disrupts signals on lower frequencies more than on higher frequencies. So that's what the sudden ionospheric disturbances such as solar flares. All right, so all frequencies are not created equal. All right, approximately how long does it take the increased ultraviolet and X-ray radiation from a solar flare to affect radio propagation on Earth? So remember, we said that this thing is traveling at the speed of light, so it gets here in 8 minutes time. Okay. How long is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes, right? Well, HF communication is disturbed as the answer. Next question. How long does it take a coronal mass ejection to affect radio propagation on the Earth's surface? So this is not a solar flare that's traveling at the speed of light that gets here in 8 minutes. These are particles that are traveling at a very high speed, but it's from a CME, or coronal mass ejection. And it takes anywhere between 15 hours to several days. Next question in the question pool. What is a geomagnetic storm? It is a temporary disturbance in Earth's geomagnetic field. Next question. How can a geomagnetic storm affect HF propagation? Well, it can degrade high latitude HF propagation. Okay, so that's how it can affect it negatively, but the next question now is how can it affect it positively? How can high geomagnetic activity benefit radio communication? So we said auroras, it creates auroras that can reflect VHF signals, and of course hams will try to utilize that property. Next question, what does the K index measure? So remember we talked about the A index and the K index. So the K index measures the short-term stability of the Earth's geomagnetic field. Next related question, what does the A index measure? The A index measures the long-term stability of Earth's geomagnetic field. All right. So again, Earth's geomagnetic field, yeah? All right. What does MUF stand for? Okay, so it's the maximum usable frequency for communication between 2 points. And now, what does LUF stand for? So LUF is the lowest usable frequency for communications between 2 specific points. And we want to know what factors affect the MUF. So we gave those factors and we said in the question, the answer will be all of the choices are correct. So path, distance, and location is one. The time of day and the season is another. And then solar radiation and ionospheric disturbances is the third. So all are correct. Those are the factors that affect the maximum usable frequency. All right. How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF? Well, this is actually what we are trying to achieve. This is highly desirable, right? We want to utilize the ionosphere with frequencies below the MUF and above the LUF because they are refracted back to Earth, and that's what we're trying to do with our signal. We're trying to bounce it off of the Earth, and that's why we are trying to choose frequencies that's actually below the MUF and above the LUF. Okay. What happens to radio waves with frequencies below the LUF? Right? What happens to it? If you have a frequency that you punch into your radio and you're trying to communicate, well, not very much for you because those frequencies are attenuated before it reaches the destination. What happens to HF propagation when the LUF exceeds the MUF? Well, all right, that can happen when you have some sort of a disturbance, right? So propagation via ordinary skywave communication is not possible over the path. In other words, radio blackout. Next question in question pool. Which frequency will have the least attenuation for long distance skip propagation? So let's dissect this. Which frequency, so they want to know what frequency, will have the least attenuation, meaning the least reduction in signal for long distance skip propagation. So again, that is HF radio communication via the ionosphere. What frequency will have the least? We said that frequency will be the frequency just below the MUF, the maximum usable. A frequency just below it is the one that will have the least amount of reduction in signal or attenuation. Next question in question pool. Which of the following is a way to determine current propagation on a desired band from your station? So we said we can use the internet, use a network of automated receiving stations on the internet to see where your transmissions are being received. And we said that Pre-SK Reporter is one of the good choices. You can check it out. All right, next question up will be, how is a directional antenna pointed when making a long path contact with another station? So remember we said that we have short path, long path. So if we point it in one direction, which is the short path, if you want to take the long path, what we do is point the antenna, the directional antenna, maybe a Yagi, we point it in the opposite direction, which is 180 degrees away from the short path. So 180 degrees from the station's short path heading, right? Opposite direction to short path. Next question in the question pool. What is a characteristic of skywave signals arriving at your location by both short path and long path propagation? Well, the answer is that you may get a slightly delayed echo you might hear. Next question in the question pool. Which of the following is typical of the lower HF frequencies during the summer? We did say due to things like thunderstorms, you might have a high level of atmospheric noise or static. Okay, why is skip propagation via the F2 region longer than that via other ionospheric regions, meaning the D and the E and so on, right? Well, the reason is because the F2 is the highest layer, or highest of all of them, and it can result in a further or farther propagation. What is the approximate maximum distance along the Earth's surface normally covered in one hop in the F2 region? So we did give that as approximately 2,500 miles, 2,500 miles for the F2 region. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the E region? So again, that will be about half of the F2 layer, which is approximately 1,200 miles. Which ionospheric region is closest to the surface of the Earth? Remember we said it's D, E, F, and the F could be F1 or F2. So D is the one that's closest to the surface of the Earth, and that's the answer. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight hours? So let's dissect this question. What are they asking us? They're asking us for the ionospheric region. So that's either going to be D, E, or F, or D, E, or F1, F2. Which is the most absorbent of signals below 10 megahertz during the daylight hours? So during daylight, most absorbent below 10 megahertz, the D region. And the last question that we'll deal with this evening in the question pool, why is long distance communication on the 40, 60, 80, and 160 meter bands more difficult during the day? And that's related to the D region again. It's because the D region absorbs signals at these frequencies during the daylight hours. And folks, I think that would be it for our question pool. So let's just go back to our slide deck to give our wrap up. All right, so we have been covering pages 71 to 79 if you're following on the No Nonsense General Class License Study Guide. So this is our trusty little table, because sometimes we need to know what is HF, what is VHF, what is UHF, what is the 70 meter band, what is the 20 meter band, what is the 40 meter band, what is the 160 meter band in terms of frequencies. So hopefully this trusty table will help us as a reference until it becomes second nature to us. So folks, as usual, feel free to send an email to this email address on your screen, as well as this number is good for WhatsApp for any questions that you may have. We do have this WhatsApp group that you can join if you wish to get updates, including the links to the Zoom session, as well as additional information that we share from time to time on this channel. So you can feel free to share it as well. Right, so our next session will be next Friday. I believe that's the 12th of January, 2024. Usual start time, 8:30 p.m. So folks, thank you so much for joining this evening. We will see you next week. Take good care. Have a great weekend all. Be safe.